Hi everyone, welcome to the session on privacy. Today we will have 3 talks in person and 2 remote. And we will start with Juniper Lovato and more data types, more problems, a temporal analysis of complexity, stability, and sensitivity in privacy policies. Juniper, please take it away.
Oh, hello. Go back. Hi, I'm Juniper Lovato, and I'm a PhD student in complex systems and data science at the University of Vermont. And I'll be talking about our paper, More Data Types, More Problems, which is a temporal analysis of complexity, stability, and sensitivity in privacy policies. I want to thank my team. Philip Mueller, who's not here, but Parisa Suchdev, who's here and sitting in the front row, and Peter Dodds. Okay, so collecting personally identifiable information on data subjects has become a multi-billion-dollar industry. It profits from collecting, buying, and selling consumer information. And one of the big problems is that there's a big lack of transparency in this industry. And this makes it difficult to understand what types of data are being collected, how they're being used, and who they're being sold to. It also makes it really difficult to understand the risk that individual data subjects are being exposed to. So in this project, we take a mesoscale approach, and we analyze privacy policies over time by looking at the word, the topic, and the network levels. And we do this in order to understand stability, complexity, and sensitivity in privacy policies over time. Okay, so we started by curating an original lexicon of personally identifiable information terms, and these are 287 words that are associated with PII. So we found these definitions and list of words through close reading and manually annotating legislative text from 9 US state laws that concerned consumer data privacy. Okay. So the data that we used was the Princeton-Leuven longitudinal corpus. This is a privacy policy corpus by Amos et al., and it contains about 1 million privacy policies from over 100,000 websites ranging from 1997 to 2019. Okay, so let's get started with our results. In our mesoscale analysis, we began by looking at the word level, and we investigated turbulence of PII terms in privacy policies over time. And essentially what we did here was look at the frequency distribution of all of these terms and looked at them on a time series. Okay, so in these visualizations, which we've been calling our PII smokestacks, we pulled out some words that fit certain conditions, and this is just to demonstrate some of these frequency distributions and how people could use them. So the first figure you'll see here on the left are words that are decreasing in frequency, more than 15% in a year compared with the previous year. And these are words that sort of like go out of fashion. And in the next panel over, you'll see in the middle words that are rising in frequency, so they're gaining popularity. Next over, we look at words that we think are emerging. And then finally, we look at sort of stable words. And we see some interesting results here. So for example, words that fall in popularity over time, we're seeing some trends that these might actually be replaced by several more specific words. So for example, the word coordinate seems to be going out of popularity, whereas in the sort of next panel over, when we look at the rising words, we see more specific types of words like geolocation and latitude and longitude increasing. And then words that are increasing and rising rapidly over time, we see a lot of these are have to do with sort of indirect tracking methods. So these are kind of more ambient ways of collecting PII. So these are things like beacons and internet browsing behavior and inferences and geolocation. And for our emergent words, we're seeing these corresponding to more things like new technology, like biometric information, or health-related terms like face prints or voice prints or irises. And then for our stable words, what we're seeing is that these are mostly words that are sort of like collected directly from consumers to conduct normal business. So these are words like address and password and things that would be used in conducting everyday business. We also created a timeline of some events that happened in the US and EU that have to do with privacy legislation. And we did see some visual correlation between spikes in certain terms rising or falling over time, which was kind of interesting, but this was just a visual inspection. And in some near future and current work, we're looking at sort of more robust time series analysis to see how these correlate, not just visually. I just wanted to go over this very quickly in the interest of time, but we also can use these kinds of visualizations to query what kinds of terms appear in the privacy policies over time. So we did some thematic queries. So here we're looking at health words and words that have to do with inference. And here we're looking at genetic related words and location words, and just interestingly looking at sort of how the rise of genetic and biometric have drastically rised over time. So this was an interesting result for us. Okay, so let's move on up and go to the topic level of our mesoscale analysis. And for this, we did topic modeling, which uses a stochastic block model topic modeler. And we did this in GraphTool, which is a great tool. And we looked at topic prevalence over time. And what we see is that topics are actually pretty stable over time. And we do see some trends that are related to spikes because of maybe new technology or possibly privacy policies reacting to new legislation. But we interestingly saw similar results to what we saw at the word level, where indirect collection of PII is looking pretty popular as time goes on. And we see that cookies really dominate this topic landscape throughout the entire time frame. And then directly collected PII attributes like address and name and age show a pretty high prevalence in the beginning of this time period and then start to dwindle over time. And this actually may be because of, again, these indirect methods of tracking and sort of as ambient tracking mechanisms become more popular. And then finally, our sort of third most popular sort of topic segment are behavioral data like preferences and movements. Okay, so let's move on to our final level of the mesoscale analysis. So this is our network level, so we're really looking at it from a 10,000-foot view. So here we investigate what words are used in the corpus to see what data types are collected concurrently together. And we use a co-occurrence network analysis to represent the use of relevant terms within the same text. So the harms associated with collecting data really increases as different data types are aggregated together. Harms become more than the sum of their parts, so the data set becomes more sensitive and poses more privacy risk as data types are combined. And so we really wanted to look at how those are being combined in privacy policies. So the co-occurrence network utilizes network analysis, and it presents a relationship between objects that appear together in the same environment. And to create a co-occurrence network, we essentially add an edge between words that appear in the same privacy policy. So if they occur together, we add a weight of just one at these little lines in between the circles, which are nodes. And if two terms from our PII lexicon appear together in additional documents, we add more weights. Okay. So then we look at sort of the network density as a measure of sensitivity in these co-occurrence networks. And we do this by measuring how closely connected these networks are over time. And this sort of shows like how densely packed these PII data types are in the network. And we sort of normalize that by looking at modularity, which also accounts for the network size and the number of clusters in the network. Okay. Finally, we explore complexity of privacy policies as represented by a compression factor of the corpus over time. What we see is that the complexity of these privacy policy corpora steadily decrease over time. And essentially just the compression factor is just the bits of the minimum description length of the corpus divided by the bits of the non-compressed description. So essentially, just the smaller the compression factor is, means that the model can compress the corpus more, and like that it's more self-similar. Yeah. And I'll just note that that doesn't necessarily mean that like this means that privacy policies are more human readable. This is a machine metric, but that would be interesting work to do later on. Okay. So in summary, we find that privacy legislation might correlate with some of these trends and changes in stability and turbulence of these data types over time, that complexity of the privacy policies are decreasing over time and becoming more regularized, and finally that sensitivity is rising. I want to thank our lovely team again. And thank you all for listening. You can check out our preprint link here or our paper in the proceedings. So thank you.
Next up, we have Faisal Haman. Faisal, please come take it away.
Okay, thank you everyone for being here. My name is Faisal Haman. I'm a PhD student at the University of Maryland, College Park. Today I'll be talking about the privacy risk in algorithmic auditing. What information about people's identities is leaked when computing group-level disparities? This is joint work with Jihao Jen from Responsible AI and my advisor, Sangramita Dutta from the University of Maryland. So, as we know, machine learning has found itself in many high-stakes settings, such as hiring, education, lending, healthcare, and so on. And these models may exhibit bias towards some protected groups based on race, gender, and so on. We now have anti-discrimination laws to ensure algorithmic fairness, right? So, for example, the Title VII Civil Rights Act of 1964 introduces two notions of unfairness: disparate impact and disparate treatment. One interpretation of this law is that a model might avoid violating disparate treatment if it explicitly doesn't use the protected attributes during training. However, we know that these models might still be liable for disparate impact due to proxies in the dataset, such as zip codes and so on. In fact, existing literature demonstrates that one may use these protected attributes during training to mitigate disparate impact. So, in fact, the use of protected attributes during training still remains a source of active debate, right? On one hand, these protected attributes can be used to account for biases, know which subgroups are affected, audit, and so on. On the other hand, they can be used maliciously. For example, they could be used to mask discriminations. In some settings, anti-discrimination and privacy law completely prohibits the use of protected attributes during training. For example, in finance, institutions cannot ask individuals for their race while having to still show that their models are non-discriminatory. So fairness assessment when these protected attributes are unavailable is extremely challenging. Due to this, institutions often adopt a separation between model developers and a compliance team to ensure that anti-discrimination and privacy laws are met. So the model developers are those who train the model. They have access to the features of the data sets, the true labels, but they do not have access to the protected attributes. The compliance or the auditing team, on the other hand, have access to the entire data set. That's the features, the labels, and the protected attributes. So after the model developers train a model, they can test for bias by querying this compliance team for some certain fairness metric, such as statistical parity, equalized odds, or any measure of unfairness. So the question we ask is this method for querying for fairness enough in keeping the protected attribute hidden from leaking to the model developers? Well, not exactly. We can demonstrate this using a canonical example using statistical parity. We know statistical parity or demographic parity can be written as an expected difference in prediction among two population subgroups. So now consider two models that have the same prediction on the entire data set except for one targeted individual. So in this setting, assume this person is the first individual in the data set. So the statistical parity of these two models would reveal the protected attribute of that one single targeted individual. So in this case, we have this difference in SP between the model would reveal the protected attribute of that one individual. So our first contribution generalizes this idea, right? We are able to write the statistical parity queries of different models as a linear combination of the protected attribute, right? So here, SP vector is a vector containing the, say, statistical parity of all the models. H is a matrix containing all the predictions of all the models across all the individuals in the dataset. And V is an unknown vector that represents the protected attribute. So if this matrix here is full rank, then the protected attribute of the entire test dataset can be identified by simply solving a linear system of equations, right? Or simply, you need as many queries or as many models as the size of the dataset to be able to recover the protected attributes in the dataset. Well, one might say this is too many queries since some datasets are extremely large, right? So our second contribution leverages compressed sensing to be able to recover this protected attribute with fewer number of queries. So provided that the size of one group is much smaller than the other, which is usually the case when you have like a minority group that are actually the minority. So we convert our original problem into a compressed sensing problem, and we have this sparse vector S here. We show that provided one group is much smaller than the other, then using compressed sensing, you can retrieve the protected attribute at an order of log n number of queries or log n number of models. So that's log n of the size of your data set, which is much fewer than an order of n in the previous setting. So our results pose an interesting question in algorithmic fairness or auditing. Should querying for these fairness metrics be viewed as a neutral valued solution to ensure compliance with regulation? Or does it constitute a violation in privacy if the number of queries is enough to leak the protected attributes? To address this proposed violation, a possible solution is to leverage differential privacy when releasing fairness queries to the model developers. So for example, the Laplace mechanism would add noise calibrated from the global sensitivity of our fairness metric to achieve epsilon differential privacy. However, when we do this, we notice that answered queries are usually too noisy for the model developers to be able to have any information about the models they're querying for. So how do the compliance team answer useful fairness queries without leaking this protected attribute? So our third contribution leverages the smooth sensitivity framework to achieve epsilon differential privacy. The smooth sensitivity framework was introduced in Nassim's paper in 2007. You can think about it as an intermediary term between the local sensitivity and the global sensitivity. And we see that when we do this for a given privacy parameter epsilon, attribute conceal achieves much fewer fairness error compared to Laplace mechanism while at the same time preventing protected attribute leakage. We provide experimental results over a broad range of parameters, sparsity, test size, n. But in general, the takeaway is just that we see a trade-off between the fairness query error and our leakage, which is consistent with existing literature because we see a tension between privacy and fairness in general. So to summarize, we show that querying for fairness metrics leaks sensitive information to the model developers. We introduce a differentially private technique called attribute conceal that calibrates noise to the smooth sensitivity of our fairness query. Our approaches assume that both the model developers and the compliance team hold the same test data set. But however, this might not be true in every context. When the auditing team holds a different test data set, it can sometimes not be a true representation of the training data set, which can sometimes affect generalization. We also make a distinction between leaking protected attribute and inferring protected attribute. For example, if the model developers know a feature is highly correlated with the protected attribute, say hours worked by week, is highly correlated to, say, the race, then it is possible that they might be able to infer what the protected attribute is. An interesting scenario for future work will be to leverage a synergy between leaking the protected attribute and inferring the protected attribute, and questions about how that might affect the regulations in privacy. And thank you very much.
Next, we have an online presentation from Maciej Krzysztof Zuziak.
trained any possible implementation just by imposing too rigid formalization of the concept. And then, of course, there is a minimal utility that we have defined as collaborative computation. So generally, we are still in the domain of machine learning and data analytics. We are creating that data collaborative because we have different actors interested in training one model or performing one or more analytical operations across the whole collaborative. So without the ability to do that, we cannot consider something a data collaborative. And here is the perhaps something that I also want to highlight, that the basic definition of collaborative computation is something that was defined in a way that is as open and as abstract as possible. So generally the only prerequisite here is that we have a selected number of participants in the collaborative. Each of them should be able to run some analytical operation, and then we should have a method to gather those operations and either aggregate them or distribute them across all the actors of the data collaborative. And one can see data collaborative as a kind of extension of the currently available methods for distributed learning, and I will use those last 2 minutes to just give an overview of the example, of the exemplary case, when we have different hospitals in the network. Some central orchestration node deployed by a third party is sending propositions to those clients across the network. Client can join or refuse the proposition. If the client accepts the proposition, then I will make the example more simpler by saying that we are using federated learning and we are delivering the weights to the clients that have accepted the proposition. And now we are able to train the models. And after that, using some pre-chosen algorithm, for example, federated aggregation, the simplest vanilla case, those actors that participate in the collaboration are in possession of one model that was learned on their data without the direct sharing. And by training this model, we have now established a collaborative, and we can further enforce the guarantee schema, for example, for model recreation or model of if we want to discard the model. This could be done by the popular vote of all the members of the collaborative. And those are some chosen references, and while of course in 10 minutes overview of the whole concept is rather difficult, I highly encourage to take a look at the final paper and see the expansion of the idea, as especially on the technical side, it is much more clearly explained there in the original paper. And I wanted to thank you all for hosting me today and for giving me opportunity to deliver this rather brief talk on this very interesting concept.
Next up, we have Yuxin Chao.
Hi everyone, I'm Yuxin and I'm a PhD student from MIT. Today I'm happy to present the paper titled In the Name of Fairness, Assessing the Bias in Clinical Record De-Identification. And this is a joint work with Sulamite, Tom, and Marzia. Recently, as reported in many scientific journals and public media, machine learning has made great advancements in healthcare applications. On the one hand, these advancements rely on the increased availability of clinical data sets. On the other hand, the legal sharing of these clinical data sets requires the de-identification of protected health information. So in the first place, what is de-identification? Let's consider an example of electronic health record, where the record contains the patient's name, age, and other protected health information. Then de-identification tools aim to unmask 18 types of PHI according to the requirements of the HIPAA safe harbor provisions. If done appropriately, prior work finds that clinical data sharing adds significant value to scientific reproducibility at low risk to patient privacy. Existing de-identification methods are reported to perform well on average. However, the question is, do they perform equally well on all demographic groups? What if these tools fail solely because of the associated demographic attributes? We know that that would be unacceptable because it would lead to severe consequences, including the violation of laws, the exacerbation of existing bias, and many more. Therefore, in this paper, we focus on investigating the bias in de-identifying a specific PHI category, people's names in clinical notes. To that end, we assess the demographic information associated with a name along the following 4 dimensions. The first dimension is gender, where we consider male and female groups. The second dimension is the expected racial or ethnic identity of a name, where we consider white, black, Asian, and Hispanic groups. The third dimension is the popularity of a name, and we measure the popularity by the absolute frequency of a name across the entire population. The fourth dimension is the decade of popularity. And in order to evaluate the impact of a demographic dimension, we design experiments to control for the other dimensions. For example, when assessing along the dimension of race, we only consider names of each racial group that are of medium popularity in the 2000s. Now that we are aware of the set of experiments we need to run, I would like to introduce how we constructed the 16 name sets used in our experiments. We compute the popularity of the first and last names based on the US Social Security and Census data sets respectively. We then select names that are primarily associated with a self-identified racial group with a margin over 10% based on a mortgage application data set. In order to assess along the dimension of race, for instance, we pull the results of name sets 3 and 4 for the white group, 7 and 8 for the black group, 9 and 10 for the Asian group, and 11 and 12 for the Hispanic group. Once we have the 16 name sets, we follow this figure to set up of our experiments pipeline. More specifically, we manually created 100 clinical node templates based on real-world hospital discharge nodes. We marked the names and replaced other PHI categories with realistic synthetic values. Our templates are more analogous to real-world de-identification challenges with an average of around 13,000 characters and 3.5 unique names per template. For each name set, we duplicate each of the 100 templates 10 times and fill in 4 names randomly generated from that name set. This creates a total of 16,000 nodes for evaluation. Based on these evaluation nodes, we examine 9 public and private de-identification baseline methods, including 3 off-the-shelf NLP libraries, 3 commercial services, and 3 open-source toolkits. To quantify the bias, we introduce the recall equality difference, which is the average absolute difference between the recall of each demographic group and that of all the groups are considered along the corresponding demographic dimension. This metric demonstrates the difference in recall each group would experience while expecting the reported average performance. On this basis, we aim to investigate the following 3 research questions in this paper. Is there demographic bias in these examined de-identification methods? What causes their underperformance? And can we mitigate their bias? And the short answer to the first question is an unfortunate yes. Let's look at their overall performance in terms of precision, recall, and F1. We can see that FLAIR performs rather well, probably due to its use of document-level features. NeuroNER also attains competitive scores, possibly because it is pre-trained on clinical corpora. On the other hand, SPACY gives the lowest recall, albeit its popularity. Google also underperforms compared to the other 2 commercial platforms. We know that this is probably because we chose Google Cloud Data Loss Prevention API, which to our belief was the only option suitable for de-identifying names in clinical free text. And this API was not specifically designed for the clinical corpora. We then look at the demographic bias in these methods, which is measured by recall equality difference as lower is better. An asterisk next to a bias score indicates a statistically significant difference in a method's performance along a dimension. And we can clearly see that a majority of these methods exhibit statistically significant gaps along most dimensions. Such disparities call for urgent review and action. Amazon and Google gives the highest bias for name popularity and the decade of popularity, respectively. Although NeuralNER performs well in F1, its bias is rather high, especially along the dimensions of race and popularity. In contrast, Filter has very low bias since it's rule-based. FLAIR achieves not only the highest recall, but also relatively low bias along all 4 dimensions. Next, we take a fine-grained look at the recall of the demographic groups along each dimension by each method. We highlight that these methods act very differently along the dimension of race. Stanza and the NeuralNER attain very low recall in the Asian group. The 3 commercial services also perform worse in the Asian and Black groups. Moreover, the performance of most methods deteriorates with the popularity of names, with the exceptions of Stanza and Mist. We also examine the recall at the level of each individual name set, averaged across the examined methods. We observe that the average recall of the name sets with top popularity outperforms the other sets with a clear margin. In addition, even the least popular names associated with the white group score higher on average recall than the more popular names associated with the Asian group. For the second question of what factors contribute to the underperformance, we look into polysemy names, gender consistency, and certain template characteristics. We observe that names with the lowest recall usually have other meanings in English. For instance, the word Cleveland in Cleveland Spikes is both a large city in the US and also a first name of medium popularity for Black males. Consequently, we would like to evaluate the de-identification methods on this type of polysemy names and identify 5 polysemy first names for each of the white, Black, and Asian groups. In comparison to the original setting, we observe that for most methods, the recall ranking of the 3 commercial groups based on polysemy first names remain relatively consistent. This indicates that polysemy names expand the underperformance of these methods, but not necessarily their demographic bias, since the performance gaps persist here. Moreover, semantic context such as titles and pronouns often indicates the gender associated with the name. Therefore, we expect that methods leveraging such gender context for name recognition to have higher recall when there is gender context agreement. To determine if this consistency really matters, we identify in our templates where name gender can be easily inferred from the local context and plot the difference in recall between names that are gender consistent and inconsistent. We observe that most methods perform better on names aligned with the implied gender, and space is the only exception here, perhaps shedding light on its lowest average recall as reported in previous slides. In addition, we observe that the recall deteriorates with both the length of a node and the number of unique names that it contains. And we also identify the 2 hardest templates in terms of recall, templates 86 and 67. Unlike usual templates such as template 50, the two hardest templates both contain large blocks of medication history that provide little indication for the names that intersperse them. We believe that this is a unique characteristic of clinical record and needs special attention in future identification systems. To answer the third question of how to mitigate the bias, we propose a simple and method-agnostic solution of fine-tuning the methods with clinical context and diverse names. In the first place, let me introduce the setup used in our fine-tuning experiments. We consider 2 types of of context, general and clinical, and identify 2 types of names, popular and diverse. In this way, we end up with 4 fine-tuning setups. Then we use our manually created templates and the remaining names to construct the testing set. We examine the effectiveness of the 4 setups by experimenting with 2 methods that behave distinctly out of the box, where spaCy exhibits a low recall and moderate bias, while NeuralNER achieves high recall and high bias. Despite the distinct out-of-the-box performance of the 2 fine-tuned de-identification methods, the setup composed of clinical context and diverse names largely enhances the overall performance of both methods and diminishes their bias along the dimensions of race and popularity. We argue that this fine-tuning setup could be an immediate fix to improve fairness before applying the methods to clinical tasks. Next, I will briefly discuss the implications of our results. First, the demographic association of names suggests that the Chinese datasets of ML models may implicitly contain bias through names and therefore require careful audits. Second, machine learning models may unintentionally learn the bias in healthcare datasets and consequently further escalate the unfairness in downstream applications. Third, as recommended by prior work, legal and ethical data sharing should be encouraged. Fourth, it is not acceptable to exclude some populations from de-identified data sharing. Fifth, we note that disparities in de-identification can lead to poorer privacy for marginalized populations and engender crimes such as identity theft. Last but not least, we highlight the importance of audits in making changes, especially in the field of healthcare. Thank you for your kind attention.
Thank you, Xin. Next up, we have Arushi Gupta, and unfortunately, I don't get to present the Best Paper Award in person, but let's congratulate the speakers for the next paper.
Hi, I'm Arushi Gupta, a research assistant with the Stanford Reg Lab. I'll be presenting on the privacy bias trade-off, data minimization and racial disparity assessments in US government. This is joint work with Victor Wu, Helen Webley-Brown, Jen King, and Dan Ho. On his first day in office, President Biden signed Executive Order 13985 to advance racial equity. The executive order requires all federal agencies to conduct equity assessments to, quote, assess whether underserved communities and their members face systemic barriers in accessing benefits and opportunities. However, as the EO itself notes, many federal datasets are not disaggregated by race. The lack of demographic data is a product of 50 years of data minimization at a federal level. The government limits data sharing between agencies under the Privacy Act of 1974 and direct data collection under the Paperwork Reduction Act, implementing the idea that agencies should collect and retain only data minimally necessary to achieve their objectives. We call this tension between data minimization and the desire for equity assessments the privacy bias trade-off. While technical literature has engaged with the tension between fairness and privacy, looking, for example, at how differential privacy worsens model accuracy for marginalized subgroups, the impact of data minimization in the federal government is far less recognized. Our paper systematically studies the privacy bias trade-off across federal agencies. First, we conduct in-depth case studies of 10 high-volume agencies and survey the 25 equity action plans submitted as agency responses to the executive order mentioned earlier. Second, we summarize the data collection methods considered across agencies. Third, we discuss the types of barriers to acquiring demographic data. And finally, we conclude by offering policy recommendations. Our review of 25 agencies' equity action plans revealed that 21 recognize that better demographic data is essential to meeting equity goals. For example, HHS says, quote, HHS currently lacks the data and equity assessment capacity to consistently identify and address inequities in health and human services. The USDA builds on the lack of data to add that, quote, where it is collected, there is not always enough knowledge to put the data to use. Similarly, IRS both struggles to collect data and, quote, laws against disclosure prevent IRS from acquiring the information from other government agencies. Beyond the basic recognition that demographic data is needed, we observe which data collection methods each agency considers. Sample surveys refer to surveys of a subset of the claimant population, form collection to the addition of demographic data questions to agencies' existing paperwork, record linkage to cross-agency data sharing, typically with census, imputation to the process of inferring race from name, location, and other collected characteristics, and finally, visual observation, where employees visually determine claimant's race. We found that 15 agencies mentioned some expansion to data collection programs, though these proposals are of varying specificity and seriousness. Here, green signifies a relatively developed proposal. We also see that the most frequent modes of proposed data collection are form collection and record linkage. We distilled 5 types of barriers from these case studies. First, legal restrictions like the Privacy Act explicitly prevent agencies from collecting or sharing demographic data. While exceptions to the ban exist in law, bias assessments don't fit neatly into any of the standard carve-outs. In a survey of 79 officials from different federal agencies, 47 respondents cited statutes prohibiting data collection as a barrier. The most frequently reported barrier by 66 respondents was, quote, regulations and policies that make it difficult to link data. These regulations and policies refer to internal guidelines for data collection and sharing beyond the letter of the law. Given the complicated legal landscape, agencies often struggle to understand what exactly is legal. So even where statutes don't ban data collection or sharing outright, internal policy takes a conservative approach that becomes a cognitive limit to expanding data sharing. Second, we turn to the political risk posed to would-be collectors. That is, when agencies consider expanding data collection requirements for third-party providers like banks, these third parties sometimes react by raising privacy concerns. For example, the Consumer Financial Protection Bureau issued guidance in 2018 expanding demographic data collection requirements for mortgage lenders. This guidance included privacy protections, stating that loan-level data should be modified before public release to prevent individual borrower re-identification. But some industry commenters still stated that the CFPB should only release aggregate-level data, or not release any data to protect borrowers' privacy. The CFPB's report paraphrased industry comments as arguing that, quote, if there's any chance that Home Mortgage Disclosure Act data could be used for criminal purposes, the benefits of disclosure could not outweigh the privacy risks. Next, agencies sometimes worry that directly asking for demographic data will elicit a negative response from the public due to unfamiliarity with existing privacy protections, a lack of awareness of the collective benefits of demographic data collection, or distrust of the data collectors. Even if individual privacy is not substantively threatened and collection would be permitted by law. When the justification for data collection under privacy law is murky, agencies are especially likely to behave conservatively to maintain public trust. Agencies that already struggle with non-response are particularly suspicious. For example, SNAP does not want to risk lower enrollment by requiring race and ethnicity, so demographic questions are optional. But voluntarily provided data is not statistically meaningful if non-response is non-random. SNAP and other food security programs used visual observation until 2021 in an attempt to supplement voluntary response. While recent guidance from the Food and Nutrition Service bans visual observation, it does not offer an alternative to bridge gaps left by voluntary response. Finally, we look at the technical limitations of legacy systems, limited provisions for interoperability, lack of technical expertise, and administrative burdens that can make data collection and sharing costly. These limitations exacerbate the existing resource gap. The USDA's Market Facilitation Program is one example of technical limitations. Even though visual assessment was prohibited by departmental regulation, because agency staff could not progress through the data management software used without completing the race and ethnicity field, more than 2/3 of responses, or over 500,000 responses, were based on visual assessment. The VA, on the other hand, has significant data stores, but as UCSF notes, VA data are maintained by several distinct data stewards, leading to a sometimes confusing alphabet soup of data partners. Given sufficient resources, the VA could consolidate its fragmented technical landscape to combine existing data sources and evaluate their programs. And in their Equity Action Plan, the VA suggests just that, proposing the Data for Equity Data Hub. While privacy protections are essential, as our case studies illustrate, the current landscape of data collection leaves us without the information necessary to implement EO 13985 and address racial discrimination in the federal government. We will conclude with an overview of some potential paths forward. First, Congress can enact an explicit exception to the Privacy Act to allow record linkage for the purpose of bias assessment. This exception is similar to existing carve-outs for national security purposes or statistical analysis. Second, agencies can internally separate their enforcement offices from those that conduct equity assessments. Thus, enforcement officials will not receive demographic data, and the agency can allay fears of race-based discrimination to build public trust. Treasury is implementing this tactic already. The Office of Tax Analysis is pursuing bias assessment of tax benefits and does not share the data with the IRS, which actually conducts audits. Third, the federal government can increase investment in technical infrastructure and promote cross-agency initiatives. Programs like the recently instituted National Secure Data Service are a good start. Fourth, Congress can amend the Paperwork Reduction Act to streamline the process of adding demographic data questions to federal forms. At the moment, each agency must undergo a separate notice and comment process. Fifth, to address public concerns, federal data collectors can explain how demographic data will be collected, used, and protected on forms to encourage higher voluntary response rates. While data minimization as a policy is broadly viewed as a success, our analysis highlights real weaknesses. Concerns about the government gaining knowledge of individuals has reduced visibility into the impact of policymaking on subgroups. We hope these suggestions can be a starting point to ensure that we can continue to protect individual privacy while still enabling bias assessments. Thank you. If you have any questions, please feel free to share them with us. Thank you.
All right, let's thank all the speakers for their insightful presentations once again. If you have any questions, there's a mic here. Please stand up and approach the mic. And can I also invite all the speakers to the stage so they can answer the questions? So maybe I'll start with a question for Juniper. You mentioned that the complexity measures that you looked at do not tell us much about the readability by humans. Is there methods, or are there methods in complexity science, network science, that could help us get at understanding the readability?
That's a good question. So the idea that I have around this would probably be to try to compare and see if there's any correlation or association with readability scores and these complexity measures. That's a really good question. I'm not sure. There are lots of NLP tools for readability of different levels of high school or whatever, what the text sort of aligns with. But we didn't explicitly do any of those comparisons. But I think it could be really cool to do that. Thanks.
Maybe now the question for Faisal. The framing of your work is that we have the one party that is the model developers, and then the other party is the basically internal audit compliance team. I know that at CSCW this year, they came out another paper that also uses differential privacy to try to prevent the leakage of privacy, of sensitive information, but they look at the framing of external auditor, where it's not like a team within the company, but an external team. Do you think that your approach also works in that case? And if so, if there's any additional considerations?
Okay, yes, thank you for your question. So yes, we're aware of the framework where you have an internal, say, an institution, and you have an external auditor, and that auditor might not have the data set, right? They just want to see that your models are fair, right? So we will need to make some changes to our assumptions, but you can think of our model developers now as an institution and the auditors you can think of our model developers as the auditors and think of the auditors in our paper as the institution, and you don't want to leak sensitive information to outside auditors in that scenario because you say your company you have approval from the users that not to leak their information to outsiders. So yeah, it would extend with some assumptions. Thank you.
All right. Yushin, I have a question about whether you maybe interacted with any of the companies that operate these algorithms that you audited. Maybe did you let them know about the problems you encountered, and did you get any feedback, any interactions?
Yes, thank you for the question. Yes, like indeed, we talked to Microsoft recently about like whether like how we can eventually improve their methods, and also like since now that with the advent of GPT-4 and the ChatGPT, then like we are also interested in auditing whether those generative language models are a good tool for like de-identifying the clinical records. So we are indeed like making this progress right now.
Great. Are there any questions from the audience? And if not, let's let the thank the speakers again. And